So let's continue on and talk about adding and subtracting radical expressions. Like radicals, what we're really talking about here are like terms. So radical like terms have the same, and what we're going to say is index, which is going to be square root and square root, and then there's something called the radicand. And when we're looking at square roots, the number that goes right there is called the index. Ours is typically an invisible 2 when we're talking with square roots. The content underneath the square root sign, or the radical sign, is called the radicand. So what that's going to mean is something like this. If we've got some amount of, let's just say, square root of x, plus some amount of the same square root of x, what's really going to be happening is that we're going to add those a and b terms together and leave the x the way it was. And same thing when we're working with subtraction. So when you look at this at first, it might seem complicated, but what's really happening is something just like this. If I gave you 3x plus 4x, you would tell me that that answer is 7x, because you simply added the 3 and the 4. Notice that the x didn't change, though, because when we're adding something, such as 3 apples plus 4 apples, we know that the answer to that is just 7 apples, right? The variable doesn't change. It doesn't turn into apples squared or anything like that. So when we have 3x plus 4x, it's 7x. So here, if I have 3 of square root of 5x, and then I have a 6 of the exact same thing, all we're really doing is saying I have 3 of something, I have 6 of that same something, so I have 9 of that value. Now, what you have to be careful with, though, is when you look at examples like this, to where it's 4 times the square root of 5 minus 3 times the square root of 3. These are different. If I was to give you 4x minus 3y, there's nothing you can do. That would already be the answer. And this is also already fully simplified. There's nothing else I can do when the square roots are not the same. The square roots must be the same for us to be able to put these together. This one can go together because we have square root of 2 and square root of 2. So here we will get a 7 square root of 2. Number 4, you might recognize right away, the square root of x and square root of y are not the same. This is already the simplified answer. Now, what you have to be on the lookout for is scenarios where it looks like things are not going to be able to be simplified, but after we do some work to them, they will be able to be simplified. Now, when you look at this, you'd say, oh, well, square root of 27 and square root of 48 are definitely not the same. But if you apply some simplification to those two individually first, you'll realize that something happens. 27 can be simplified to a 9 times 3, to where we square root the 9 to get a 3, square root of 3. The 48 can be shrunken down to 16 times 3, where we can square root the 16 to get a 4. And then there is already a minus 2 square root of 3 there. So after we did simplifying, you'll see that we do have square root of 3 for all of these. So once we get that, all we're really talking about now is 3 plus 4 minus 2, right? Because we have 3 of something plus 4 of something minus 2 of that same something. So 3 plus 4 is 7. 7 minus 2 is 5. We have 5 square root of 3. These make for really good ACT questions because this answer looks strange considering what we started with. You always have to simplify and check to see if they are like radicals. So on these up above, there was nothing I could do. Like on this one, square root of 5 and square root of 3 can't be simplified, so that's why that was the final answer. X and Y can't be simplified to get the same radicand, so that's why that was the final answer. But on other ones, you have to be on the lookout because they will look different at first, but after you simplify them, they might be able to go together. For 18, we have 9 times 2. For square root of 32, we have 16 times 2. We can square root the 9 to get a 3. We can square root the 16 to get a 4. And we're left over with square root of 2 for both. So 3 of something plus 4 of something gives me 7 of that same something. So always just be on the lookout using your perfect squares to help simplify expressions. This one's 9 times 7. So here we'll get a 3, square root of 7. And when you're given problems like this and you know that they're potentially going to simplify, what I'm going to do is I'm going to go ahead and just divide 175 by 7 to see if, when I do that, I even get a number that's going to work. Because I know that this one had a square root of 7 left over, so I'm assuming that this one might too. And when I divide it by a square root of 7, it does. It's 25 times 7. And then I can square root the 5 to get 5 square root of 7. And then we have 3 minus 5. That's a negative 2. So always be on the lookout to try to simplify these before you add and subtract them, or see if they can add and subtract. If you struggle on finding pairs, you'll get better at it as you do more and more of these. Anytime you see a number like this, or on this last one, like 175, multiples of 25 are pretty easy to spot. This one's 25 times 10. And the square root of 25 is 5. So we have 5 square root of 10. And then on this subtraction, we have square root. Hopefully you recognize that there's a 4 in there, and there's a 10. You can square root the 4 to get a 2. So we have 5 square root of 10 minus 2 square root of 10 together to give us 3 square root of 10. So that's how you add and subtract. You have to first simplify to see if you can get the exact same radicands, and then you can add and subtract those coefficients out front. But really it's no different than adding apples and apples. Multiplying binomial expressions. This is where we're just going to be using FOIL, and we'll also have some square roots going on. So you just take it one piece at a time. 3 times 1, it's 3. 3 times square root of 5 is just going to be 3 times square root of 5. Because what's really going on is this 3 doesn't have a square root, so it's going to just multiply by the invisible 1 out front. So we get a 3 times square root of 5. Here we have a square root of 5 times 1. And then here, square root of 5 times square root of 5, remember that when two things are multiplying and they're both square roots, what you're really doing is multiplying those inside pieces. So now here, I have 3 of something and 1 of something, so it'll add together to give me a 4 square root of 5, and the square root of 25 is just 5. So here we'll get an 8 plus 4 square root of 5. These also make for good ACT questions because when you're looking at this, 8 plus 4 square root of 5 is a little bit of a visually different answer than what the original problem looked like, so these problems can really throw people off when they're really not that complicated, especially when you go step by step. So 3 times 2 is 6. Here we'll get a negative 3 square root of 6. Here we'll get a negative 2 square root of 6. And then here we'll get a negative times negative to get positive. Square root of 6 times square root of 6 is square root of 36. And then you simplify what you can. Here you'll have a minus 5 square root of 6. The square root of 36 is a 6. So we'd end here with a 12 minus 5 square root of 6. So all we've been doing on this 7.4 properties of radicals is just working with square roots, adding and subtracting them, multiplying them. And as mentioned back at the start of this, these are important concepts. You use them a lot in geometry, where you'll be working with triangles, and the triangles will have square root values for the side lengths, and you'll need to multiply them when you're using the area formula. You'll use it when you're finding the distance between 2 points. A lot of times that will end up as a square root. So this was just to help us get prepared for the oncoming resurgence of square roots in mathematics. You'll be adding and subtracting them, multiplying them for the different formulas, so this was to help get us ready.